Everyone, thanks for coming, and thanks for giving me the opportunity to tell you about ID01, right? So this is one of the beamlines of the ESRF, which is really partially dedicated to coherent diffraction. And so I'll tell you a little bit about ID01 over the last sort of 6 years, because it was rebuilt in anticipation of the ESRF EBS being developed. And then I'll show you a few results of what we've done so far. And all of the results I show you today are done by a huge team of people, right? So I'm just officially the messenger. So this is what our end station looks like, right? On ID01. So we have a very big hutch. Inside that hutch, we have a diffractometer, and then we have this huge pipe which can rotate around out of the screen, right? And so this allows us to access Bragg peaks. And so typically we're doing microscopy or imaging of Bragg peaks, so we're sensitive to the lattice, right? And so we produce a variety of images. So typically 3 techniques, but we can also do more, right? And so we have to make compromises on our experimental setup as a result. And so one of the techniques is basically nanodiffraction, right? So we focus the beam down, we put an optic in close to the sample. We focus the beam down as small as we can, and we raster it across the sample. We measure one of these Bragg peaks and see how it changes as a function of time. So in this specific example, you see a ferroelectric thin film with some electrodes on top, and at some point we're going to apply a field and we're going to see the domains that are underneath these electrodes switch around, right? So you can do this. The resolution is limited by the optic that you use to focus the beam, right? So typically like a zone plate or something around the order of 100 nanometers. Now a similar technique to this one, well, we're looking at a large field of view here, right? So up to 100 microns square. A similar technique in terms of resolution is full field diffraction microscopy, okay? So this time you move the lens from in front of the sample to after the sample and directly image the Bragg peak that you're interested in, right? You don't need the coherence for this, and you can measure large fields of view and still get similar resolution because it depends on the focusing optic. Now, one of the most interesting applications for the beamline is using the coherence of the beam to surpass effectively the problem of making a good X-ray lens, right? And that's using coherent diffractive imaging. So instead of a lens, we use a computer to reconstruct what the crystal looked like, and we can recover the strain inside the object in 3 dimensions, right? And so I'll focus on this as I discuss the rest of the beamline. So what I forgot to tell you is that we're a very long beamline because we want to make very small beams, right? So we're 120 meters from the source. And when we put our lens to focus it down, it means we have enough working distance between the lens and the sample that we can put some kind of environment there. So we can take these crystals and then do something to them and see how they behave in their normal working environment. So what does this look like schematically? Upstream, there is very little, right? There is a synchrotron and there is a monochromator, right? So typically, we just use a mono. We don't even use a wide beam mirror because it's not very stable, right? And so we simply pick an energy with our mono and we let that propagate down the beamline. At some point, we put in some slits to define the coherent part of the beam, which you can calculate very easily from the source parameters. And basically that coherent volume that you then have, so the longitudinal coherence, I didn't say, is set by the monochromator. As long as it's bigger than the crystal, then the chances are the diffraction pattern is going to be nice and coherent. So you can calculate what these values should be. And on ID01, at least before the upgrade, you had about 70 microns in the horizontal, 370 in the vertical. And with the new source, this is increased in size, right? Significantly in the transverse directions. What doesn't change is the longitudinal direction because this is chosen by the monochromator, right? And this is always the limiting factor. So for us, it's about 0.6 microns. What you typically do, because these transverse coherence lengths are so large, is we put a focusing optic here to condense the beam to get flux density on a crystal, which is sort of a few hundred nanometers in size, right? And so you gain flux density of sort of 4 to 7 or 8 orders of magnitude this way. What I didn't mention, or I forgot to mention, is so this silicon 111 monochromator has a bandwidth of about 10 to the minus 4, right? And so this 600 nanometers is sometimes too much, depending on what you want to look at, right? And so on ID1, we have another option. That is, we have a multi-layer monochromator. And this gives us a bandwidth of about 0.3%, right? And so this gives us a flux gain of about 20, in addition to whatever the new source provides. So this is an option for looking at very small crystals to boost the intensity on our sample even further. Right. So what kind of beam sizes do we look at typically on ID01? So somewhere of the order of 30 nanometers up to a micron in size for the nano diffraction, coherent diffraction, and we take the full beam for the full diffraction. Since the upgrade, sort of our distribution of beam time between these techniques has changed a little bit. Obviously, it's more focused on the coherent diffraction side because that's what the new source is very interesting for. And the kind of flux that we expect on the sample should increase by about a factor 28, right? And we're typically getting somewhere of the order of 10 to the 10 photons for the nano diffraction and 4 times 10 to the 9 for the coherent diffraction before the upgrade. And there's also the opportunity to look at higher energies. And maybe I'll discuss that a bit further later. So if we zoom in a little bit on our end station, right, so you can see what our diffractometer is really capable of. And we have our sort of two normal setups, right? So we have a KB mirror system, which is kind of a very efficient focusing optic. It produces beam sizes of sort of 200 nanometers up to a micron in size. And the alternative is a set of zone plates. And we've now decided to back this set of zone plates up. So the zone plates produce very small spot sizes with a set of CRLs, which sit behind with a long focal length and provide the option of having either a small beam with a zone plate or a big beam with high flux and equivalent flux density through the CRLs. And we zoom in a little bit closer to the sample position, and you can see that we have quite a lot of room to put environments, right? And so I think I even put the measurements on. So we have a microscope typically looking down from above on the sample if we can see the sample through whatever environment we're looking at. And we have a little auto sorting aperture sat on the end there to clean up the beam that comes out of our KB. And so the stack that you see here is just a piezo 100 micron stroke in 3 dimensions, sat on top of a hexapod, which gives us our coarse motion. And then you have the goniometer to rotate the sample and the detector arm for the detector. The detectors we use on the beamline are MaxiPix and Eiger detectors, both in silicon. So the types of sample environments you'll typically find on ID01, right, vary. So we have furnaces. These are all homemade at the sample environment group. So they're 3D printed furnaces in the reflection geometry, transmission geometry. We have the opportunity, the possibility to use cryostreams, cryostats, electrochemical cells, strain rigs, and so on. So there's really a lot of flexibility in what you can put on the beamline and then deliver the beams to these environments to do your experiments. And right now, the top right, I don't know if you can see it because my head might be in the way, there's an AFM, which is actually being mounted on the beamline today. So when you come to do an experiment on ID01, what do we try to do, right? We try to make the experiment as successful as possible. And the way we do that is we really tried to learn in the last 6 years how to characterize our end station and understand our beam, right? And so the first thing we always do is we do ptychography on a reference sample, which is just a Siemens star. So I'll probably end up showing you far too many of these today, right? But you see, basically, you don't just reconstruct the object, but you also reconstruct the probe, and you can start to see problems arising in your optics, should they be there. And then once you've done that, you can then go ahead and put a sample on and go into the Bragg geometry and start to do some experiments, right? And so here is just an example of a few of the beams, right, that we've had over the ESRF over the past few years, right, and they really vary quite a lot. And all of the reconstruction software, for most of the examples that I'll show you today, are made using the PyNX Python library, right? So this was developed by Vincent Favre-Nicolin at the ESRF, and it's really revolutionized the way that we do our experiments. So in 2015, users would come and take the data blindly and then go home and then analyze it later, right? And now we're at a stage where really you can take the data and within a few minutes have an idea of what the crystal you're looking at really looks like, right? And so this really changes the way that you can do your experiment. So why do we do this every time? So here's an example of what our compound refractive lenses look like when you raster a small slit across them, right? And see how the beam changes. And we found out, this is only a couple of weeks ago that we discovered this, but we actually have a really bad region on the stack of CRLs that we used that week. And so we can pick a nice beam to use for our experiment this way. And this is quite important because obviously with the increased flux from the EBS, we're starting to see damage on some of our optics. So then we go, and now we've got a beam, we can actually go and do a measurement, right? And so typically we take a standard sample, something like this, and we'd align it in the beam using a relatively consistent method, right? So we put this on, and then you can use the scanning diffraction to find what you're interested in finding, right? And we've developed a lot of tools on the beamline to make this process very easy for the user. So they will do a scan like so, and literally click on a crystal, and then you can do a count and you can find out what this thing looks like, and then you can go to the thing that you really want to measure, right? We spent a lot of effort in making all of the things that we develop publicly available, right? To stop people from reinventing the wheel. And we can move forward together. So that's great. So that's basically how we do an experiment. So what are the kind of the results that we've been generating? I've chosen a couple of highlights just to show you that are currently in submission or very close to submission. So this is coherent diffraction imaging in situ or in operando, right? So this is a platinum crystal, like the one we kind of saw on the first page. In this case, it's during a catalytic reaction, so the conversion of carbon monoxide to carbon dioxide. And what you see is that in this particular case, we have just a portion of the crystal. There's actually more crystal on the side, but you can't see it because it's a twin and it diffracts to somewhere else in reciprocal space. And you see that as you change the conditions that this crystal is living in, basically the crystal changes size, right, which is a bit bizarre. And it's a twinning effect. So one twin is eating the other twin, right? And as you continue through this process, you can actually start regrowing the twin again in this case. There's also lots of other things going on. So because you have this resolution and you can see the strain evolve as a function of these conditions, you can see facets forming and changing, right, while this is all taking place. So there's lots of sort of interesting things that you can discover. But this is sort of a typical experiment that you can expect from something done at ID01. Now, from the scanning diffraction side, I thought I'd quickly show you just an example of something that may, in the future, not quite yet, really benefit from the coherence, right? So this is a ferroelectric thin film. And again, it's the same image as was shown in the first slide, where you have this electrode on top, right? And you have a set of domains under here, which we're going to change when we apply a field to them. And we can see them switch, right? The resolution that we have here is defined by the beam size because it's scanning diffraction. And we're not actually seeing individual domains, but we're seeing what are called super domains, so clusters of domains that are all oriented in the same direction. And so what the hope with an experiment like this is you can then use the coherence to effectively surpass the resolution set by the beam and maybe even resolve these domains one day. And so this isn't limited to just static imaging, right? Sort of on off, you can also go through the whole hysteresis loop, right? And start to see different areas of the sample, start to switch at different times and understand why this is the case. So they're just a few highlights of sort of everything that's been going on at ID01 and before the EBS, right? And then the EBS came along. So what does the EBS really mean for ID01? So if we look at the old source size, right, you can see that there's a source of 25 by 120 microns and a divergence which is pretty large in the horizontal direction and relatively small in the vertical. And so if we look at our end station where we put our zone plates, so here's our focusing optic, right, the beam would look something like this if you drew a cartoon, right? It's actually a lot wider and just couldn't fit on the screen. And then you get an idea for what the coherence aperture, the slit that we put in front of the optic is, right? So there's really a lot of photons here that are just not used. And so when you add the ESRF EBS, basically the source size goes down, so this slit gets larger, and the divergence goes down, so the beam also shrinks, right? So we just end up in this situation. So we just push loads more photons into this coherent slit. So we should have a huge number of photons to use for our experiments. It should equate to about a roughly 28 increase in flux. And so if we put a beam viewer, this is about 100 meters along our beamline. The old ESRF, we couldn't see the sides, and EBS, we can see the whole beam very clearly, right? And as this propagates down the beamline, we start to see some of the coherence effects, right? So the image here is basically the whole beam in the experimental hutch. It's sort of about 2 millimeters across. It's in log scale. And then you have some fringing here already, right? So this is actually a safety aperture that we have in the beamline that's now been moved. So that's gone away. And then you also have some kind of coherent feature producing fringes on the detector. And this is actually sat, the thing that's producing this is on the double crystal monochromator. So when you drive this around, you find patches of the crystal which are cleaner, and this no longer exists. So just an example. So now we have this beam. We should try to at least clarify that the parameters are what they said they are, right? So the beam divergence we can measure very simply by scanning the slit, so it's very close to what was suggested. But we also have a set of optics halfway down the beamline, some brilliant lenses that can allow us to condense the beam onto the sample position, and we can image the source almost 1 to 1.1, right? So we do that in the vertical direction, which is not touched by any of the optics of the beamline because our DCM is horizontally scattering. We measure a beam size, a source size very close to what they suggested would be the case. We're not quite measuring it in the horizontal direction. We only did this measurement last week, so we're still trying to understand why this is not the case. But in any case, the things seem to be where they should be from the source side. So then we tried to do a little bit of a flux check, how many photons are really coming down at ID1. And so we did this before with the old ESRF, and we had something of the order of this number per square micron, right, in a certain bandwidth. And then when we did it with the EBS, we only got a factor of 10 out. And we then realized that we forgot to put in one of our undulators, right? And when we did that, we managed to retrieve most of the intensity. So the way we did this was we just have a slit. It's about 100 microns from the source. It's very nice. We close it down and we measure the diffraction pattern on our detector in our hutch 20 meters away. And then you can do the reconstruction and find out what the slit looked like, and then just divide the intensity by the area, right? And you get your flux density out. This is not the photon flux that will make it down to the sample, right? Because we have a horizontally scattering double crystal monochromator, you lose a lot due to polarization at lower energies. And there are also other things in the beam, right? So we have windows, we have air gaps, and so on and so forth. And obviously focusing optics, which aren't completely efficient. So just to give you an idea of the different beams and roughly how many photons we deliver on ID1 today, right? So the zone plates produce the smallest beams with EBS, and we're around the sort of the 10 to the 9 for the really tiny beams. So this is a 24 by 29 nanometer beam, or with half max, right? Up to a few e to the 10. CRLs for the bigger beams, up to almost 10 to the 11. And then the KB. Now, unfortunately, our KB is a bit compromised at the moment. So if we could use it all, we'd be able to get up to sort of 1 to 2 times 10 to the 11 photons. But we have bad regions on it, and there's clearly damage. So we're looking at ways to, well, we're basically going to replace it. But we still use it at the moment, just with fewer photons on it. In reality, what I'll come to again later is that we have so many photons that a lot of the samples can't take it, right? So we don't need it all. So just a comment on the very smallest beams that we produce. So the zone plates that we have to produce these came from PSI, Frieda Koch and Christian Love's group. And this is where we start to see the stability of ID1, right? And we're very lucky because we don't have any interferometers in our hutch. And we start to see vibrations only with beams of 30 nanometers in size, right? So it gives you an idea of what our vibration level is, right? And it's very, very low. So we're very lucky because we don't have any way of knowing what it actually is for the moment anyway. And then the EBS really came, right? And so last year was a bit disrupted for obvious reasons, right? And so we lost a lot of commissioning time, but we still took users at the beginning of August last year, right? And so our first users came from the group of Felix Hoffman. So we had Nick Phillips doing an experiment trying to exploit the high energies. And since then, we've had 13 user experiments, right? And we're continuing to do as many as we can in remote operation. Yeah, to give you guys as much of this beam as possible. In the meantime, we've been doing some commissioning, right? So what have we been doing with all of this flux? And I'd like to give you 5 examples, right, of situations that have arisen, right? So the first thing is we've destroyed quite a few things with all of these photons, right, from crystals to optics. So I'll just show you. So if you put this is one of Nick Phillips' samples, right? So this is just a gold crystal, about 150 nanometers in size. And if right now we're filtering the beam by about a factor 40. And as we take the filters out, you can just watch the diffraction pattern and you'll see that it starts to evolve, right? And so it's slowly starting to wobble. And this crystal eventually comes loose and falls off of the substrate. And we can't see it anymore, at least in diffraction. The good news is that, I mean, you can see that the scattering goes a long way, right? The resolution is very high in a very short time. So it's very encouraging if you can get your sample to sit still. The other advantage of having almost too much flux for this particular example is that typically we have crystals nearby that scatter in similar places, right? And this is a problem. It's we call them aliens, right? And so what you can do is you can go along and you can hit these with the full beam and you can make them move, right? And you can get rid of them before you finally do your measurement. So this is an example of one taking off and disappearing, right? So we do one of our little 2D maps and we find all of the crystals that are nearby that are causing problems and we just go and shoot them, right? So we can do the measurement on the crystal we want with filters in. A more worrying problem is when the crystal itself is changing, right? So this is an example actually before the EBS of just a very thin gold sample, which just changed as a function of time when you put it in a beam, right? So we have no idea what's actually happening when you put this much flux into these crystals, right? And if we're actually measuring something that is interesting, or if we're actually measuring a beam interaction with the sample is really a question that's going to have to be solved. So other destruction, so we've broken one of our beam viewers along the beam line because there's just too much flux. We've hit the detector pretty hard a couple of times, so we have to be a lot more careful, right? And we've also seen damage on our optics. So one of our zone plates has been destroyed. You can see that all of the zones have just collapsed in this zone plate, right? And this is pretty punishing. If we're losing optics quickly, we have to be very, very careful.
I fear, unfortunately, we are losing the connection with Steve.
It's the ESRF network.
Like 1 degree of rotation, right? And so there are several things to consider, right? So you have
Even we lost the last minute. We lost 1 minute talk.
You lost the last minute? Can someone else confirm this? Or it's just...
Yeah, we couldn't hear you since the zone plate was melting.
Oh, okay. Is it working again?
We just want to hear about the melting zone plate again.
Yeah, you're back.
Okay. All right. So basically, this zone plate, we ended up accidentally just above the absorption edge of tungsten, right? And this resulted in basically the zone plate dying very, very quickly. And you can see in the shape of the beam profile, right, how it's now distorted along this direction for some reason. It's not clear where this comes from. But in any case, yeah, that's now no longer used. But there's an opportunity here, right? With all of these photons, we can actually save ourselves in other sides of the problems that we face for doing these measurements. So we can tune the beam size a little bit, right, according to the experiment that we're doing. So typically we put a nanocrystal in the beam. It's a few hundred nanometers in size, and the beam is a few hundred nanometers in size. And so you rotate this crystal in the beam, and you want it to stay in the beam the whole time. If it falls out of the beam slightly, right, this is going to lead to some kind of asymmetry in your diffraction pattern, and this shows up for us as strain, right? And so we'll effectively see an artifact and interpret that incorrectly. So in order to approach this, we ask the question, did the crystal stay in the beam for the duration of the measurement? And in order to do that, we have to care about a few things. So we care about end station stability, which we've already seen, right? Our vibration level is very, very low. We also have a good handle on our drift, or the stability of the sample. And we know that it's of the order of 60 nanometers an hour when we close the hutch for a few hours. So then it really doesn't become a problem anymore. Beam stability is also pretty incredible. It really doesn't move. So this is ruled out as a source. And then it just comes down to the combination of beam size, crystal size, and sphere of confusion, right? And you can crudely say that like the beam size minus the crystal size has to be greater than the sphere of confusion to get the best data quality, right? So if you're detector limited, right, which for the majority of our samples we are, right, because we look at slightly larger crystals, then you can reduce the flux density on the sample a little bit, make the beam a little bit bigger to make this win for you, right? And we've had a couple of instances which seem to suggest that maybe this is a really good thing, right? So I'm going to show you some pictures from an experiment from Maxime Duprat and Marion Goodrichard. And so they were looking at nickel crystals, right? And so you can already see from the diffraction pattern that there's a lot of strain going on here, right? It's extremely asymmetric. And at least in the past, we've never managed to get anything like this to remotely phase when doing the reconstruction. If you throw this, well, they threw this into PINX during the beam time, and it just spits out the result, right? I mean, you can see there are huge phase variations inside this crystal. It nails down the support really well, and you have really clear, distinct structures. So these are two separate crystals. It wasn't just one specific crystal. It was in a good situation, and it also works for multiple Bragg reflections. So we were looking at different Bragg peaks for each of these crystals, and they all seem to reconstruct very, very well. So we are very surprised by this and also very encouraged. We're not sure if it's really a case of the beam being a bit bigger, but it definitely helps us, right? Having all of these extra photons. And then you can look at it in 3D, right? And you can see the displacement field that's going on inside this particular crystal, and the phase range we're talking about here is greater than 20 radians, which is really something that we don't normally see work. The obvious thing to tackle with the new source is to try to make the crystals that we look at a little bit smaller, right? Because we have all of these extra photons. We can increase the flux density on the sample and target smaller things, right? So typically before the EBS upgrade, we were looking at maybe things down to sort of 100 nanometers in size. And so the example I'll show you is from, again, work from Marion Ingrid, working alongside people at Oregon University. So they provided a sample of platinum crystals. These ones aren't going anywhere. They're embedded in sapphire, right? So they're really stuck there. And so we found one of these that was about 22 nanometers in size, right? And we were able to put I think it's about a 17 nanometer beam on it, rotate it through 3 degrees and measure the full rocking curve of this thing, right? And so you can start to see what the data looks like. It's not as pretty here because I think this is just a 1-second exposure. If we look on the next page, we see a slice through a 50-second exposure. So there you can just count the fringes to guess roughly where the resolution is, but we're hoping that it's somewhere of the order of 3 nanometers in a 22 nanometer crystal. And this particular measurement is not optimized yet, right? So we're talking about a few times 10 to the 10 photons in a 70 by 70 nanometer spot. And so there's still room for improvement in this. The zone plate is not very efficient, right? So if you're producing a similar spot with a KB mirror set, you'd win. We could also talk about changing to our different monochromator, right, to increase the bandpass and get 20 times more flux through onto the sample. So there's definitely opportunity here for looking at small crystals, but you've got to have a small crystal that is really stuck, right? And eventually it's got to be stuck in a position where you can do something useful to it whilst it's stuck. So the fourth thing to say is that the beam is pretty coherent, right? So I gave you an example of nano diffraction, and effectively because of the aperture of all of our focusing optics, most of our experiments are now coherent experiments, right? Because the focusing optic is pretty much almost coherently illuminated. So you can start to think about Bragg ptychography. So we did a test last summer with the help of Virginie Chamar's group at the Institut Grenoble, and the key person behind this is Peng Li. He did the analysis. He's now a postdoc on ID13. And so this is a silicon Siemens star, right? I don't have an actual picture of it, but we don't need it because the X-rays are going to show us, right? And so we effectively do ptychography at many angles, and then you compute what the thing looked like, and here's roughly what it looks like, right? It's a bit distorted. The drifts haven't been considered yet in this reconstruction, but you get an idea of what it should look like, right? And that there really is hope here for ptychography in the future, kind of taking over these scanning diffraction methods. One of the goals of this particular test was to do it online at the time of the experiment. And so I'm not sure if this is, this might be slightly tweaked, but Peng was able to produce this image during the beam time, right? So this is very encouraging. This particular scan is in step-by-step fashion, which is a bit slow, so it's still, I think, a 4-hour acquisition. But he was also able to do it with a fly scan mode. Again, the distortions are going to be a little bit larger here, but it's clear that eventually it will work. And so all of the stuff that I've shown you has been pretty much done around 8 or 9 kV, right? But there's also the opportunity at the EBS to go to higher energies, because the flux is, I think, equivalent to the old ESRF at 8 kV and about 30 kV. And so we haven't really done this on ID1, but we have done it on ID31. So here's an example. About 10 days ago, we finished an experiment where, again, we were looking at platinum crystals, right? So this is the diffraction pattern of a platinum crystal at 41 kV. Right, and so the parameters for the flux that are delivered to the sample, like 3 × 10⁸ photons, in a rather large spot, right? So this is not optimized, so there's still a long way to go here. And the data acquisition time is about 4 minutes for what looks like, I think if you count the fringes, something like 25 along one of these streaks. And so you're looking at kind of 30 nanometer resolution on a 600 nanometer object. And so I'd like to thank the ID31 team for doing this stuff, right? It was a tough experiment. And then everybody related, right? So the last 6 years has required a lot of work, and a lot of people have been responsible for everything that I've shown, and I have to thank them, right? And so here they all are in various states. And I'd like to thank you for your attention. And if you're interested or you want to ask any further questions, contact me directly, right? We also have a beamline wiki, which is available to anyone with an ESRF password, a user password, so an SMIS account. So don't be afraid to find out more about the beamline. And that's it.
Thank you so much, Steve, for this overview. Now the session is open for questions. So to ask questions, you can either unmute yourself, it's got a liberal environment, or you can raise your hand, or you can write it in the chat. I see that there is already a question from Angel in the chat. He was asking about the thickness of your gold layer in the experiment you've shown. Is a few hundred nanometers, or is more about a micron?
Oh, that was about 40 nanometers.
40, okay.
Yeah.
Angel, do you have any comment on this, or you're happy with the? Well, you can let us know. I'm actually curious.
Happy.
Yes, thanks. I have a question about your KB. Unfortunately, it's damaged, and I think it's going to take a little bit of a time for you to get back. But do you have any specific plans for your optics? You want a flex, like a bendable mirror, so you're going to go for?
So right now we have a bendable KB, and very much looking towards fixed curvature, effectively very similar to the one at Nanomax, right?
Yeah. I would really advise this, actually. I mean, obviously there is a drawbacks on this choice, but I think that the stability, what you gain in stability and eventually in ease of alignment, I think is tremendous. So
yeah, so right now when we put our KB on, it takes us a good 8 hours to get it aligned, which is very painful, and when we align it, it doesn't look very nice.
And do you have a sense of the stability, how long this alignment is preserved along the experiment?
Days. The alignment is very good, but the mirror surface is not very good anymore.
So I see.
I don't have a slide on this presentation, but basically if you do ptychography on day 1 of the experiment and then 6 days later, there's very little difference in the beam. Okay.
I see Gudrun raise their hand. Please, Gudrun, unmute yourself and ask your question.
Hey, good afternoon, everybody. Stephen, thank you for the nice talk. I have one question. I saw at the user meeting that ID01 has recently measured a tooth sample, 20 micrometers thick. Could you maybe comment how good this biomaterial sample survived your beam? Was it already measured after the upgrade? Thank you.
No, it was measured, I can't tell you when, but definitely before the upgrade. As far as I'm aware, there's no radiation damage. I can't tell you any more than that.
Okay, thank you. So you think it survived ID1 conditions?
Yeah, at least that experiment was just scanning diffraction, right? So you're rastering the beam across the sample very quickly. So each part of the sample receives very little dose.
Okay, thank you.
There is a question from Ana Diaz, and she was asking about the large phase shift in the reconstructed Siemens star by Bragg ptychography. That's a critical eye.
Yes. Yeah, so, well, I mean, there's a large phase shift, right? What can I say?
Can I answer, Stephen?
Yeah, you can go for it.
Thank you. Hello, and it was a very nice talk. I enjoyed it very much. So hi, Anna, hi, Dina. Hi. So the phase shift, so the Siemens star, we call it a Siemens star, but actually it's a pattern that was designed into a silicon substrate, the usual one that we are using. And this phase shift is a result from the strain induced by the patterning. And actually, we have done a similar experiment at Nanomax beamline with Dina, and the phase map is pretty much the same. And we have also confirmed this with electron transmission microscopy, at least with EBSD actually. So this phase shift is really real, and it's fully related to the strong geometrical ratio you have between height and width and so on.
Okay, thank you.
You're welcome.
Thank you, Virginie, for commenting on this. We have another question from Angel, and Angel asks about how do you locate the compound refractive lens or the Fresnel zone plate after the sample? I think, Angel, you're talking about the microscopy setup.
Yes, exactly.
So how do you align?
Along the Bragg direction or diffraction direction.
So I go back to the picture of the beamline, right? So we have this big pipe with our detector in it, right? And so when we're doing this particular experiment, we're not using the diffractometer arm, right? So we can actually mount the lenses on the diffractometer arm and use that to drive the lenses into our Bragg peak quite easily. And then on there, we stick a hexapod, which holds the CRLs or lens stack. You can align it quite quickly.
Do usually like the vibrations of the diffractometer affect this kind of studies or not?
Good question. I don't think we've seen any impact of the vibration. I think the resolution that we achieve in these kind of images is sort of 150, 200 nanometers for CRLs. And when you use them as a focusing optic, you generate a spot size of about that, right? So we're not really seeing any vibration induced by the diffractometer.
Thank you.
We have another question from Ulf. He asks about the multi-layer mirror. Do you think is becoming obsolete after the EBS flux increase?
Not at all. If you want to look at small crystals, right, it can give you an extra factor of 20 in your flux density on the sample.
So you keep using it.
It's just optimizing it, right? So I mean, right now we typically use the silicon 111 because we have crystals up to kind of 500 nanometers in size. If you want to go down to like 50 nanometers and below in crystallite size, then you need more photons, right? Because the scattering scales with the square of the volume, right? And the volume decreases very, very quickly. So you need this if you really want to look at small things. How small you can really go and get useful information is it's not very clear.
Okay, thank you.
The diffraction pattern that I showed of a 22 nanometer crystal seems to be reasonable, right? In reasonable timeframes.
Okay. So I'd like to invite everyone just to overcome shyness and ask questions. I think this is a very nice opportunity to discuss with a beamline scientist with experience, and technical questions or scientific questions are welcome, or comments. I do have a question about the ferroelectric material that you were measuring. You said you have done some maps. I think it's a constant bias that those maps that you show. So I was wondering if you're using at all, you know, the time resolved setup that was at ID01.
Not at all. We haven't investigated time resolved yet on these kind of samples. So for time resolved, you need reversible switching, right?
Mm.
And these samples do not produce reversible switching, so we can't do it.
Yeah, well, it also depends on how high frequency acquisition you can have, because then you can just cycle with a certain frequency your device and then just measure with a higher resolution and then reshape your data. In this sense, is not stroboscopic. Yeah. Mm-hmm. And then you were mentioning about, you know, eventually you can go to coherence. What is missing to go to? Is it a matter of flux? Is quality of?
It's the data analysis, right?
Okay.
That's the only thing that's missing. I think the Bragg ptychography data analysis has to be easier to use, and yeah. So right now, at least in PyNX, we're not there with the Bragg ptychography yet, right? The group that's most successful is Vergini's group, right? And so they're really the people that have been able to reconstruct Bragg ptychographic data. So far, I'm not aware of anyone else that is really able to get this going.
I think this is a nice message to push a little bit towards the data analysis. We have already raised the question. Virginie and then Carlos. Virginie, please.
Yes, I wanted to ask you about Bragg ptychography. I was assuming that this might be something you want to pursue, to continue. And I was wondering whether you have thought about trying to explore different kind of illumination. Like, I don't know, either curved illumination or speckled illumination, these kind of things. Is it something you are considering?
We haven't tried it yet. We would be interested in trying it, sure. I think we've had
It was not a proposal, it was just really a curiosity from my side, actually.
Yeah, we haven't thought about it, right? So okay. There's, at least from our side, we see that, I mean, people do nano diffraction, right? So they are scanning the beam across the sample, and the beam is coherent. So in principle, they should be able to improve the resolution of the images that they're generating, right? And the only way to do this is to improve the tachographic retrieval. Right?
Yeah, okay. I know.
Thank you. Carlos Sato from Sirius.
Yeah, I'm working. Okay. No, just for curiosity, you mentioned that you the possibility to change the beam size or to better fix for experiments, tiny crystals, bigger illuminations. How exactly do you change the illumination? I mean, you presented a lot of optics options in your beamline,
Yeah.
which is quite impressive. Here we don't have that. But do you only change the optics, or you, I don't know, change the depth of focus? Because I don't work with ptychography, so I'm wondering if you change the focus, would you introduce some phase into the illumination that may make it hard or make things more difficult? So
yeah,
how do you change the beam size?
Yeah, right. So you can do it by moving along the focal length, right? So you move out of focus. We used to do this before the EBS. We don't really do this anymore. Now what we do, because we have so many photons, we just aperture the optic, right?
Oh.
Blow the beam size up if you want to, right? And this is just because we have so many more photons. We can do that without compromising the stability of the setup. Okay.
Now, just for curiosity, when you
I mean, in an ideal world, right? I don't know if you saw the talk, the last talk about this atomic beamline, right? You have this this fantastic KB system which allows you to tune the beam and keep all of the photons in that beam, right? I mean, this is the ideal situation where you maintain all of the photons in whatever size beam you put on the sample, right? But we have to make a compromise, and our compromise is just to simply aperture the optic.
Okay. And another question more related to curiosity. You said that you sometimes use your full beam to move particles away. You ever really check that you are moving your particles, or you are maybe just destroying it, or I don't know?
Well, we don't know, right? I mean, you're probably just making them tip over or something, so they're diffracting elsewhere. So you don't care anymore. They're probably not being shot off of the sample.
Thank you.
Okay, I noticed that Ross had muted himself. Ross, do you have a question?
Well, I'm more interested in all the stuff you're breaking, right? So was that Yag crystal broken by a mono beam?
It's the multi-layer mono beam.
Okay.
So it's a little bit more photon.
And then what's the zone plate in? Is it sitting in air? Do you have it in an environment?
It's in nitrogen.
In nitrogen, okay. And it's a tungsten zone plate.
Yeah.
Wow. That's exciting.
Okay, we have
your
another
mirrors
question.
are in helium, right? Is that right?
No, our mirrors are in nitrogen as well.
Oh, okay. Is there a reason for that choice? Or?
Well, so helium's a bit special in France. You can't waste it, so you have to have a pretty special system to retrieve as much of it that you use, right? And so we've already considered it, at least in the initial design. We just have nitrogen.
Okay.
There is a question from Lucas. I congratulate with you for the great presentation, and he asks if you have typically problem with the stability of FFDM. Now I have to apologize, but I just cannot make this acronym. What is FFDM?
Oh, FFX, full field diffraction microscopy.
Okay, thank you.
I'm really not the expert on this. Maybe Tobias wants to comment if he's still here.
Yeah, I'm still here.
You're welcome, Tobias.
If you can hear me, yeah, actually, for the same reason Stephen said before, right? Our instrument is now so stable, right? We're seeing vibrations. We can make vibrations visible with a 30 nanometer beam, but the amplitude is below 30 nanometer. In full field diffraction, our resolution is typically 200 nanometer, so we haven't really observed stability issues on that level yet.
Okay, thank you.